So in this system here, I've got a weight falling down to the ground, which is 0.4 of a kilogram, and there's some tension in the string here, and it's pulling as it falls down this weight here, which weighs 0.3 of a kilograms, and there's a coefficient of friction on this slope here giving us 1/2. So that's the friction due to the thing sliding along the surface. Now the incline is giving us this angle alpha, and all we know is that the tangent of alpha equals 3/4. And what's been calculated, that the acceleration of the system is 1.4 meters per second squared. Now we've got these 4 questions to answer. We need to calculate the tension in the strings, and then after half a second the string breaks. So then as the string breaks, this Q is going to fall to the ground, and P, as it's already got some speed and some momentum, is just going to gradually slow down. And we want to find the velocity of P at the start of this phase. How far does it travel in the phase, and how long does it take for it to stop during the phase? So let's go about answering these questions one at a time. So first of all, let's calculate the tension in the strings. So the easiest place to calculate it will be this one here, where it's completely vertical. So we've got T going on the opposite direction, so that's minus T, and we've got the weight of the block being pulled down by gravity, so that's 0.4 times G. So that's 0.4 G. And then that was set that equal to, by using Newton's law of motion, force equals mass times acceleration, the mass of the block, which is 0.4, and acceleration, which is 1.4. So that's our force equals mass times acceleration. So just write that there. Force equals mass times acceleration. So then if I get this T on its own, bring that over to this side, and then I've got 0.4 times 9.81, and then I'm going to subtract 0.4 times 1.4. Well, 4 14s are 56, that's going to be 0.56. So minus 0.56. So plugging that into our calculator, we will get approximately 3.364 newtons. So that's the answer to the first one. We've got the tension in the string. Now what happens after the string breaks? Well, the easiest one to calculate first is probably going to be the velocity. But in the case of these 3 style of questions where you're looking for velocity, time and distance and so on, you're going to need the SUVAT equations. So I'm going to set them up over here. So SUVAT. So at the start, what's happening at the start. Let's write down our values. So time, what's going to happen at time? Well, it's been travelling for half of a second. So after half of a second. Acceleration, what's the acceleration at the start? Well, that's 1.4 meters per second. And the velocity, we don't know yet, so we'll leave that as a blank. And U, the initial speed, well, we can find out what the initial speed, because at the start of the phase it's going to be going 0 miles per hour. And then S, that's going to be the distance travelled. Okay, so we've got a couple of unknowns. We've got the acceleration and the time. So we can get velocity from that for sure, because we've got V equals U plus AT. So let's use that. So velocity for part 2. So for part 2, we use V equals U plus AT. So U is 0. A is 1.4 and T is 1/2. So therefore V is going to equal 0.7 meters per second. So that would take care of the velocity. So that's part 2. Okay, now we need to work out how far it travels in this phase and how long does it take to stop. So now as the string breaks, we're going to get a new acceleration. So the acceleration here will now no longer be viable because the thing's going to change. So we need to calculate the new acceleration. So to do that, we're going to need to work out what that is. So what I'm going to do is I'm just going to take this part of the the diagram out and work out what the actual velocity is. So if I've got that there with my block, that's my slope and that's my alpha. So what I want to do now is draw a normal line to the block and then a line straight down. So I've got my perpendicular line, I've got my line straight down, and now I need a line parallel to the plane. So I need to draw a line which goes along this direction. Okay, now from this diagram, that angle there would be opposite to alpha, so this one here will become alpha. Okay, so now what I need to do is, gravity will be acting on this as it's going up, and then it's going to slow down, so the force of gravity will be pulling down. So we need to find out what these two forces are, which are going to slow it down. And they will be travelling in this direction. Okay, so now how are we going to do that? Well, let's resolve for force 1. We know that tan alpha equals 3/4. So if we drew our little diagram, put our alpha in there, tan alpha is 3/4, that's opposite over adjacent, so 3/4. So from that we can deduce that the hypotenuse will be 5. 3 squared plus 4 squared is 25, square root that's 5. So then we can get the sine and the cosine from that. So let's look at F1. So for F1, so we'll have sine of alpha equals opposite over adjacent. So it's F1, opposite over hypotenuse. F1 over this force here. So it's F1 over the hypotenuse. Now what's the hypotenuse? Well, that's just going to be the weight of this pulling down by gravity. That's going to be 0.3 g. Okay, so then we can get F1 isolated. So then F1 equals sine of alpha, or sine of alpha is opposite over hypotenuse, so 3/5. So it's 3/5 times 0.3, which I'll call 3/10, keep it all in fractions, and gravity, which is given as 9.81, which I've not got written up here, but that's what we got. So that's force 1. Now we need to work out force 2. So then with force 2, we need cosine because it's adjacent. So then we'll set cosine of alpha equals force 2 over the hypotenuse, which would be 0.3 g. Now cosine of alpha, what's cosine of alpha? That's going to be adjacent over hypotenuse, that's going to be 4/5. So then we've got force 2 equals 4/5. Now there's going to be another bit we need to throw in here, which is given in by the coefficient of friction, but I've got 4/5 times 0.3 g, so times 3/10 times 9.81, and then we need to multiply that by the coefficient of friction, which will be acting on the normal force. So that'd be times 1/2. So that would be our F2. Okay, so now what we need to do to find that, we use force equals mass times acceleration to work out what our acceleration is. So if I use those two forces here, I will have mass times acceleration will be the negative of that and the negative of that, as it's going to be acting in this direction. So using force equals mass times acceleration, we need to find the new acceleration. So I've got minus 3/5 times 3/10. Well, let's just work that out. That's going to be 9/50. So it's going to be 9/50 times 9.81. And then subtract this one as well. So I've got 4 3s are 12, times 1 is 12. 5 10s are 50, times 2 is 100. So 50 over 100, sorry, 12 over 100, so that could then be 6/50. So minus 6/50 times 9.81, and that equals mass times acceleration. So 3/10 times acceleration. Now to get acceleration on its own, I need to just times both sides by 10/3. So if I times this by 10/3 and this by 10/3, we'll end up with back to the 9.81. So acceleration here will actually be 9.81. So that'll be our new acceleration. So then I put that in here, A equals 9.81 meters per second squared, but it's going to be going against the direction of travel. The box is going to be going upwards, but it's going to be slowing down. So acceleration is going to be negative as it's going to be decelerating. So now from that, we can calculate our next parts of our calculations. So we've done number 2 already. So that's 0.7 meters per second. So now how far does it travel? So we need to work out the time. So we've got the acceleration. So now we've done this from the start. Now our new calculations, if I just give us a bit of space just to put that in there. So after the start, acceleration is now minus 9.81. We need to work out how long and how far. So S and T are still going to be unknowns. Okay, the velocity at the start, well, the velocity at the start is what we're going to have here, which was the velocity at the end of the travel before, so it's 0.7. So U equals 0.7 and V, well, V is actually going to end up being 0 because this thing is going to stop. So if I put a 0 in there, so V is going to be 0. Okay, right, now let's see what we can do. So for how long does it take for P to stop? We can try and solve for T. So we can use our V equals U plus AT. So part 4. So let's just put a line into there. That's those bits taken care of. And these bits taken care of. So let's have a look at part 4. So how long does it take to stop? Well, V equals U plus AT is what we used before. So what is V? Well, V is now going to be 0. Our initial velocity is going to be the 0.7. Acceleration is going to be minus 9.81. And then we've got T, which is what we need to solve for. So now let's bring the 0.7 over this side. Equals minus 9.81 T. And then divide both sides by 9.81. So then we get T equals 0.7 divided by 9.81. In which case we'll get T to be approximately 0.0714. So that's going to be how long it takes to stop. So let's write that in there. 0.0714 seconds. So it's going to stop pretty damn quick. Okay, and then the final bit, how far does it travel in this phase? So we need an equation with S in it. So in this case, I'm going to use S equals ut plus a half AT squared. So let's give ourselves a bit more space here. So S equals ut plus 1/2 AT squared. And we just get RS. So S, initial velocity. Well, the initial velocity is given us 0.7. And then T is this one here, 0.0714. Okay, so then subtracting acceleration, so that's minus 9.81 times the time squared and a half. So as acceleration is minus, I'm going to change this plus to a minus. So I've got minus 1/2 times 9.81 times the time squared, which is 0.0714 squared. Now if you plug that into your calculator, you'll get S is approximately 0.025-ish. Now that will translate in displacement terms, as displacements in meters, that will become 25 centimeters. So that's how far the particle will travel after the string snaps. Okay.